Hello everyone. The purpose of this video is to show within Cabri how to set up the fundamental lattice set up the lattices or the grids for some of the imaginary quadratic rings or the integers of the imaginary quadratic fields. I think that's the right way of putting it. I also have Geometry Sketchpad and Cinderella 2. I think it's easier to do this in Cabri for various reasons. I prefer Cabri. Okay, we're going to 10 minutes, so got to get going here. I'm going to show of course, the simplest one first is a 3-mod form. That is Z of I. That is the Gaussian integers. Everyone is familiar, I'm sure, with the Gaussian integers. And that's just the fundamental or default grid on all of these things, so it's very easy to set up. Boom, there we go. And I'm sure everyone is familiar with what the fundamental region for Gaussian integers are. And there we go. And boom. And yes, that's the fundamental region. It's a square. Nothing much more to say about the Gaussian integers. So let's move on to the next more involved one, which would be z of 2i or z of -2, or the integers of q of -2. One of those has to be a legitimate way of putting it. I always seem to get it wrong, just the more mathematically technical people. Okay, but I think most of you know what I'm talking about. So in this case, we're going to have to dilate the plane. Okay, we're going to have to dilate it vertically. And in the case of the 2 or 3 mod fours, we're going to have to dilate it as to what I'm going to call the index of the quadratic field, which in this case will be the square root of 2. Now in the case of the Gaussian integers, square root of 1 is 1. So that's not really a dilation, if you will, assuming that we define the grid to be a unit grid or unit plane, if you see what I'm saying. Okay, so what we're going to do to implement this is we're going to apply a measurement transfer along the vertical axis of this square root of 2. Boom, there we go. And then we're all set to go. And we're just going to set up our new axes. We have the origin, the direction and distance for the real axis. If you set up the imaginary axis first, Cabri will, in fact, put the imaginary coordinate first, and that probably won't be what you want, so you got to be careful not to do that. Then we're going to set up the new grid. Boom, and that is the grid for z of 2i, or the integers of q of 2i or q of -2. One of those has to be the right way, at least I hope. Now I'll highlight the fundamental region, which I think all of you can guess is going to be, yes indeed, a rectangle, and I just messed it up. Okay, we'll try again. Okay, sorry. Oh man, this can be frustrating. Okay, boom, and boom, and boom, and boom, and boom. Okay, and I'm going to highlight the polygon and then color it in. Boom. That's our fundamental region. Not much more to say. I'm going to say a few more things in the next one, but let's move on to the next one. Time is just going on. Okay, all of the fundamental regions of the imaginary quadratic fields are all going to be parallelograms. More particularly, they're going to be squares, rectangles, or rhombuses. Okay. Now with this one, this is going to be the Einsteinian integers, okay, which are the integers of q of -3 or z of -3. How exactly to put that, I seem to always say it wrong, but I think most of you know what I'm saying. Now in this case, we're going to have a dilation and a rotation, okay, but we're going to first start off with the dilation. The dilation vertically is going to be equal, in the case of the 1 mod 4s, of the index of it. That's what I'm calling it. I'm just plugging it out of the hat. I don't know if index is used for something else. In this case, square root of 3, and it's going to be divided by 2. In this case, you're going to dilate by half the amount that you do in the 2 or 3 mod 4s. Okay, so we're going to take a measurement transfer in Cabri of this square root of 3 over 2 onto the vertical axis. Okay, that's part of what we need to do. And the next thing we need to do, we need to rotate the vertical axis, 60 degrees. Okay, that's one way of looking at it. The way I'm going to accomplish that is by starting off, I'm going to take the midpoint between 0 and -1 on the real axis, okay, and I'm going to define a vector, okay. Some of you undoubtedly know exactly what I'm doing, and a vector that goes from 0 to -1 on the real axis. Then I'm going to translate. There's many ways to this. Maybe this is the most efficient way. Translate this point, square root of -3. It's 0 square root of -3/2 by this vector, and I'm sure all of you, many of you know exactly what that point is. That point is, of course, it is. I'm going to hide some stuff here. That's what I'm doing. That point here right now is the principal cube root of 1, okay, or -1/2, -1/2 plus the square root of 3/2, okay, and that's exactly that's our principal surd. Another thing to mention here is that when you're talking about the integral basis, what they usually use, and maybe I can do this real quick, is what they usually use is they use select this point, boom. They usually use that. That would be that point on the right-hand side of the vertical axis is the principal sixth root of principal sixth root of 1. Okay, when you talk about integral basis, it's usually going to be in their first quadrant here. But when you're talking about the fundamental surd is one on the left side of the vertical axis, which is a principal complex cube root of 3. And that's the one you use to set up the grid, set up the axes and such. Okay, let's get rid of the principal sixth root of 1, and let's set up our axes. Hope we're not going to run out of time. And then we've got origin again, direction and distance for real axis, and then imaginary axis, direction and distance. You're going to hide the regular axes and set up our grid, and boom. That's the Einsteinian integers. And then we're going to show the fundamental region. Okay. Now you can see there's an equilateral triangle there. All the angles are 60 degrees, and there's a hexagon here, which all the points of which, if you will, all these whatever they're called, the points of it are all units, right? But those are not the fundamental region. The fundamental region is not a triangle. And it is not hexagon. It is this rhombus. Boom. All right. Then we're gonna boom, boom, and that is our fundamental region for the Gaussian integers. Okay. Now the thing is now next thing I want to show. Hopefully we'll have time. Is a quicker and simpler way to set up the lattice or the axes or the grid for the Einsteinian integers, but the problem is it might give you a misimpression about what the fundamental region is. I'm going to use a regular polygon tool within Cabri and on this mark, and as many of you probably can guess exactly what I'm going to do here is boom, I'm going to set up a hexagon, and then this point over here is of course the complex cube root of 3. The principal complex cube root of 3, sorry. And we're going to use that to set up the new axes. Origin, real axis, imaginary axis. Hide the regular axes, whatever, define a grid. Boom, there you go. Now, I want to do a few more, but I'm sure this is coming up to 10 minutes, and so I better stop this video. I'm sure we're running out of time.